And the idea behind these is that it turns out that rotational kinematics and dynamics, meaning rotational motion and the effect of forces on that motion, can be analyzed in a very similar way to what we've already done with linear kinematics and dynamics. So what I really want to do is start with just a comparison between linear and rotational. And what we'll see is that the quantity in linear more or less corresponds to a similarly named quantity in rotational kinematics. Now, the first one is going to be position. The symbol we used for linear position was just X, sometimes R. In rotational, that's going to correspond to angle. And the symbol you'll see used is typically just going to be theta. And the way you can think about angle, just like position is specifying a location of an object. Angle is specifying the orientation of a rotating object is basically the idea. A lot of times you just let an initial angle be zero. So it's not really angle itself isn't as much as isn't as important as knowing how much the angle has changed. Just like and the change in position we talked about was displacement, and the symbol we used was delta x. We for rotational we just call this angular displacement, and it turns out that all the quantities I'm going to introduce just have they're the same name. They just have the word angular in front of them. So delta theta is how we'd represent that. Velocity. This was v in linear motion, and we're generally talking about it in one direction, and this corresponds to angular velocity. You'll sometimes see a comparison, or you'll sometimes see the term angular speed as well. Basically, it's angular velocity without really worrying about sign. In general, you take right-handed, so I think it's counterclockwise is positive and clockwise is negative for angular velocities and displacements, but we're not really going to worry about that at the moment. So the symbol for that, a lot of people will say it's W. I don't care if you say W. Really, what it is, it's a lowercase omega. So I will call it omega, but if you think of it as W, then that's fine. Now the one we're not going to talk about as much is acceleration. This comes up in rotational kinematics, but we're not really going to go too deep into that. Um, and the corresponding rotational quantity is angular acceleration. The symbol that gets used there is alpha. Now, I want to distinguish this between alpha looks kind of like a squiggly little fish. I want to distinguish between acceleration and the corresponding angular acceleration and centripetal acceleration. When angular acceleration is basically an increase in the angular velocity. Now, if the angular velocity were to increase, that would require the speed to be increasing as well. So this would be another step up into a situation where we weren't in uniform circular motion anymore. So angular acceleration is just zero for uniform circular motion, and that's generally what we're going to be dealing with. So, this is one that's worth knowing, but we're not going to be playing with it very much. Um, Another big thing to know about is how we're going to measure angle. So measuring angle. Um, there are generally 3 units that you can measure. So 3 units of measure. Um, and the first one is degrees. Perhaps have heard of this one. The second one is revolutions. This I think is the most common, or I think not the most common. I think it can be common, particularly in real world situations, but I tend to think it's the most intuitive. Basically, it's the number of full circles traveled. When you're talking about the number of revolutions, you're talking about the number of full circles traveled in a given path. With degrees, the idea really degrees are defined in terms of revolution. It's 1/360th of a revolution. So degrees is just 360 is a highly divisible number. A lot of numbers divide 360 evenly. So it's just something easy to use that you dividing it up into that. Another thing that makes this common is it's very close to the number of days in a year. So you know the degrees it arose, I believe, in ancient Babylon. As to why it's used, it's just kind of inertia. But really, revolutions, I think, is more intuitive. And the one that's most mathematically useful is the last one. That is going to be radians. And basically, what a radian is, it is the angle defined as a ratio of arc length to radius. Okay. Now, the idea behind this, I'll just kind of show you what I mean. So, if you have a circle and you have, some angle, well, that's not so great because it's not really at the center, but we'll define the center. And you have some angle theta like this. Now, you can measure this as some fraction of a rotation. That would be fine. You can measure it as some number of degrees, which is basically kind of another way of expressing a fraction of a rotation. But it turns out it's more mathematically useful to look at the length of the portion of the circle. This is called the arc. Symbol we often use for arc is S, and compare that to the radius. Okay, so compare that to the R. So basically, in radians, how you define theta is you just say, well, okay, I'm going to take that arc length S and I'm going to divide it by the radius R. Okay. Now, what this means, this has an implication, and the implication for how you convert between these two is that one revolution that would correspond to an arc length of the entire circle. So at one revolution, the idea there is that theta is equal to S is equal to 2 pi r, because that's the circumference of the circle. So that means theta would be 2 pi r over r. The r's would cancel, and theta is 2 pi. So one revolution is 2 pi radians. Okay. And one revolution we also saw is 360 degrees. So if you are familiar with the conversion that to get radians from degrees, you divide by 180 and multiply by pi. That's correct. You can see that kind of pops out of this ratio is that 2 pi radians would be equal to 360 degrees. Now, one of the main advantages of radians is that we call it a radian, but really it's a dimensionless quantity. So if you think about this, is that both S and R would be measured in meters, and the meters would cancel out. So basically, you're expressing an angle as a ratio. Okay, you're relying on the geometry of a circle and then expressing the angle as a ratio, where there are no there are no arbitrary units in there. Now, why is this useful? Well, the point is that radians make it easy to go between angles and distances traveled. Okay, and this is super useful in physics when we constantly want to do this, when we don't just care about the angle traveled, we a lot of times care about the distance that the overall object has traveled, and being able to go between those conveniently is very, very useful. So for arc length, you get that nice little formula based on how I just defined the angle measured in radians, that the arc length, which would be a distance traveled, is equal to theta times r. Now, that's fine. That has its uses, but by far the more useful one is angular velocity. And the idea behind this is that the speed of the object in uniform circular motion. So just remembering that this is, UCM, uniform circular motion. This is going to be your arc length divided by the time it takes to travel that arc length. Okay. No big deal with that. Well, from there, what you get is really, this should probably be a delta theta. So your arc length is your change in theta between 1 and 2 points. So I'm gonna leave that as that. But if you combine this speed of the object, so that was equal to v. But if you combine the arc length formula that we just used, what we can say is okay, that means that our velocity is equal to delta theta r over delta t. Well, delta theta over delta t, these are two things we've already defined. That's angular displacement, and delta t is just time. Well, if you know the relationship between displacement and velocity, you can probably guess the relationship between angular velocity and displacement. And that relationship is that this thing is angular velocity. All right. So delta theta over delta t is angular velocity, but only if angle is in radians. Okay. Same thing is true of that one as well. This only work if the angle is in radians. So if you are dealing with radians, you can use this formula, V equals omega R. If you're not, you can't. You got to convert to radians first before you can use that formula. Okay, so that is something that's important to remember when looking at this idea. Now, this has an application and something we've talked about, and it's going to come up. But the thing I want to specify before going on to that is going to be that when talking about this velocity, this is the tangential velocity. Now when we say tangential, it's the velocity that's kind of tangent to the circle, that's touching the circle at the edge. Really, the way it's more helpful to think about this is just the speed of the object, in UCM. Okay, so that is how you convert between the speed of the object in uniform circular motion and its angular velocity. Okay. Now, as a reminder, our centripetal acceleration was defined as that speed squared over r. So it was that speed squared over r. Well, if we do a little bit of substitution in here, we can also say that centripetal acceleration is equal to omega squared r. And this is, again, for uniform circular motion, but turns out to be a somewhat useful tool for us as we go forward and start to look at some of these other things. Now, the other thing I want to talk about today is Newton's law of universal gravitation. And the idea here is that this comes up. It comes up jointly with uniform circular motion because the main phenomenon of Newton's, not the main, I mean, we'll talk about it in a minute, but one of the main explanatory power of this initially was in planetary orbits, okay? And the idea is that planetary orbits were caused by gravitational force. Like there had been Kepler, Galileo had understood a lot about the planetary orbits, but they never posited a cause. It was Newton who said, okay, the same thing that causes the apple to fall, that's his traditional, it's apocryphal aha moment, being hit by the apple. The same thing that causes the apple to fall is the same thing that causes the moon to go around the earth, the same thing that causes the planets to go around the sun, so on and so forth. Okay. And basically what this is, it's a formula for the force of gravity between any two objects. All right. Now, the formula you get, and we talked about this, I believe back in the first week, it's capital G, M1, M2 over R squared. Now, M1 is the mass of object 1. M2 is the mass of object 2. And then R is going to be the distance between 1 and 2. And then G is called the universal gravitational constant. It is just equal to 6.67 times 10 to the negative 11th Newton kilogram, or sorry, Newton meter squared per kilogram squared. Newton meter squared per kilogram squared. Now, the reason I give the units for that is to be really clear that in order for this formula to work, you have to have everything in SI. So your masses need to be in kilograms, your distances need to be in meters. Now, I say that, and you're probably just rolling your eyes, saying, he's off on his units again. Problem is, a lot of these problems they will give you other units, particularly for the distances. So, conversion between units is part of doing this work. All right. Now, I wanted to do a couple of examples with this. Common one is to show that the acceleration due to gravity is 9.81 meters per second squared using NLUG. Now, how exactly would you do this? Well, the idea is that we now have two different ways of expressing gravity. mg, and I've said before that this is only for near Earth, and that's true. But the idea is like, okay, so if we situate Newton's law of universal gravitation on the surface of the Earth, we should find that these two formulas are identical. And so what we get here is we also get that the Newton's law of universal gravitation should be, force of gravity should be G, and then mass of the Earth times the mass of the object, where those two masses are the same. These are both, mass of object, divided by R squared. Now, what is the R we want to use? Well, turns out it's the radius of the Earth. It's Newton's law of universal gravitation. People are tempted to say, well, the radius is 0 because I'm on the surface of the Earth. But really, Newton's law of universal gravitation only works. And the math is equivalent if you pretend that the mass of all the Earth is concentrated at its center. Okay, so really what you care about is your distance away from the center. Why that's the case, that's a calculus proof as to why that works. But really, that's what you're interested in. You're interested in distance away from the center. So what we do from there is we need to know some of these things. So mass of the Earth, 5.98 times 10 to the 24th kilograms. Radius of the Earth is 6,380 kilometers. Okay. This is what I mean by you not being given it in SI. Before you ever started this, what you need to do is you need to make sure to convert this to meters. So it's 6.38 times 10 to the 6th meters. Okay. Now the idea here is we should be able to set these two equal. So we should be able to say mg should end up being equal to g me times m over r sub e squared. And what we should find is that the mass of the object should cancel. So hopefully what we're going to verify is that G is equal to mass of the Earth, or little g is equal to big G times mass of the Earth over radius of the Earth squared. So that should be 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th over 6.38 times 10 to the 6th squared. Now, what I see, here's just an order of magnitude. I see about the base numbers, not the base numbers, but the the coefficient numbers, about 6 and about 6 multiplied together, and then 24 and 11 and negative 11. So that would result in a positive 13. So it's about 36 times 10 to the 13th. That's just approximate. And then in the bottom, I have about 6 to the 6th squared. So that would be about 36 times 10 to the 12th. So we have 36 times 10 to the 13th, about 36 times 10 to the 13th, divided by about 36 times 10 to the 12th. And that is going to get you about 10 when you do that. And that is about what G is. You can go through and do the calculation yourself, but it turns out that this is, in fact, correct. Now, I do want to do just one more problem. And this is using NLUG for orbits. So using Newton's law of universal gravitation, NLUG for orbits. And the idea here is that we're going to assume that orbits are approximately circular. They're not circular, but starting with that assumption to kind of flesh out this model and then tweaking that is kind of the way you would proceed with this. So starting with the simple case is fine. And if they're going if they're approximately circular, then they are undergoing universal or uniform circular motion. And that means that your centripetal acceleration is equal to either v squared over r or, well, and that is in turn equal to omega squared r. So the omega is going to be a little bit helpful. Now, the centripetal force is going to be equal to mass times the centripetal acceleration. But we also know that the centripetal force will just be equal to the force of gravity from the sun. That's the only force that the sun is exerting on these planets. That's the only thing that could be causing it to rotate. So what we can end up doing is we can just end up saying, okay, following through on this, we have mass times omega squared r. And I'm going to put a subscript on the r. I'm going to do rp, where rp is the orbital distance of the planet. Okay, so that's how that would go. Now, from Newton's law of universal gravitation, we'd just say, and I'll put mass of the planet there, that's fine. We'd say G times mass of the planet times mass of the sun over the orbital distance of the planet squared. Okay, now we'll see that the masses of the planets cancel, and we're just left with omega squared times the, and I'll move some of these things over. So it would be omega squared times radius of the planet cubed is equal to G times the mass of the sun. Now, it turns out the right side of that is entirely constant, so you can use this to set up a ratio. Now, it turns out that finding angular velocities of the planets it's not difficult, but it's not something we measure directly. Typically, what is measured directly and given? So typically, periods of planetary rotation are given. And the way this is typically it's done with a capital T. And basically it's the time of one revolution. I'll say revolution. Rotation means the spin on the axis. For orbits, we're talking about revolutions here. So time of one revolution. Now, the idea here is that in this time, the angular displacement will be 2 pi radians. 2 pi radians, because it went in a full circle. Okay, and remember, a full circle is just 2 pi radians. So that means omega is that 2 pi radians that it traveled divided by the time t it took to do it. Okay, and this is where this comes back to things that we can both measure about planets and things that were well known by astronomers. So subbing this in, what we get is we get, I'll do a planet there. We get 4 pi squared over t squared over t planet squared times radius of the planet cubed is equal to g times the mass of the sun. Now, a lot of times this gets expressed in 4 pi squared radius of the planet cubed is equal to g mass of the sun t squared, in that the basically the cube of the orbital radius or the orbital distance is proportional to the square of the period. This is actually Kepler's third law. So if you're at all familiar with Kepler's laws, this was actually Kepler's third law. But this is the relationship between some fairly measurable quantities among planets. Okay, so you can basically do this for any planet. You can also do it for moons around particular planets. In that case, it's not the mass of the sun that matters, it's the mass of the planets, the mass of the central body that matters in this case. But notice it's kind of interesting that the mass of the planets don't affect their orbital time or their orbital distance. It's their orbital distance is basically going to determine their time of revolution around the sun. So that's only a factor of how far away from the sun that matters. Okay, so kind of an interesting little phenomenon there. But I'm gonna go ahead and end this here. I think that's everything we need to cover for this section. So thank you for joining me and have a wonderful weekend.